Hi, my name is Zhang. In this video, I'm going to present our work learning ultrasound rendering from cross-sectional model slices for simulated training. Ultrasound imaging is real-time and non-invasive, therefore it becomes ideal for computer-assisted interventions. However, ultrasound images suffer from low image quality and its interpretation is often non-trivial. Image interpretation and also probe navigation requires therefore a high level of expertise. Ray tracing-based physics simulation is a state-of-the-art option for training medical students since it can provide an interactive training framework without the need of on-site supervisors and volunteer patients. It has been demonstrated that simulation based on Monte Carlo ray tracing can generate highly realistic images. However, for such an interactive framework, one often needs to trade off between image quality and computational cost. In our previous work, to mitigate this cost and quality trade-off, we proposed to recover high-quality images from low-quality but computational cheap simulation using image translation approach. We demonstrate this approach for a training simulation of the standard 20-week fetus examination. We used the Monte Carlo ray tracing framework to render B-mode images from a custom geometric fetus model. To preserve anatomical structures that are missing in the low-quality images, we also leverage information from model segmentation slices, which is rendered as the cross-section of the triangulated anatomical surfaces and stored as an index image. Furthermore, we propose to use integral attenuation map for preserving global acoustic shadows. To compute these maps, we aggregate attenuation coefficients that are matched to each tissue type along the wave propagation direction. With this attenuation map, we can turn the global directional artifacts into local property. The previous work shows promising results in enhancing low-quality simulated images. However, rendering this low-quality image still requires additional computation time and sophisticated hardware resources. In this work, we aim to completely bypass the rendering step and generate simulated high-quality images directly from segmentation and attenuation map using deep learning. We formulate this problem as an image-to-image translation problem, where segmentation and attenuation maps are considered as source domain and high-quality image as target domain. Our translation framework is based on pix-to-pix conditional GAN. The generator maps segmentation and attenuation input to high-quality B-mode image. And discriminator here is a patch GAN and trained to discriminate between generated and our target samples conditioned on input. We train network on randomly cropped image patches. The training loss consists of a cross-entropy GAN loss and L1-based data fidelity loss. In our previous work, we used a unit-like generator with skip connections, and we refer this model to LSA2H. Our first attempt is to use the same network architecture and remove the low-quality image in the input. To provide stochastic means for random speckle texture generation, we replace the low-quality image with a random noise image, and we refer this baseline as NSA2H. We observe very suboptimal results here. The original network in this case fails to preserve fine structure details in acoustic shadows and cannot generate faithful speckle textures. Since the low-quality image provides information about wave interactions and speckle textures, omitting this modality certainly renders translation tasks more challenging. To address the issues that we observed here, we carefully inspect the generator architecture and propose several architectural changes. First, instead of transposed convolution used in the previous work, which are prone to checkerboard artifacts and therefore not suitable for texture generation, we enhance the coding blocks by introducing additional stride 1 convolution layers, which help to prevent low and high frequency artifacts. Another change of the generator backbone is that we reduce the receptive field. We use 4 pairs of down and up sampling blocks instead of 8 pairs to preserve the local information. Since the integral attenuation map helps to transform global acoustic shadow effects into local features, embedding the entire scene in a very low dimensional feature is conceptually not necessary here. To further improve structure preservation, we also provide the input information at each intermediate layer by concatenating the input maps along the channel dimension. This way enables network to generate location-specific features. Finally, we also studied a different way of noise injection for ultrasound texture generation. Instead of using a random noise image in input, we perturb the feature channels of the coding blocks using additive Gaussian noise with learned per channel weighting. And this way of noise injection has been first proposed in Steigen paper and achieves very promising results in generating stochastic fine details. And we refer the final model as SA2H. To show the effect of proposed architecture changes, we have conducted ablation study for each component separately. Let's first look at some qualitative examples. The top row shows the target B-mode image with its segmentation and attenuation map overlaid on top and bottom corner of the image. The second row shows the translated results of the final model. By ablating the input attenuation map, the model fails to generate acoustic shadows, for example, those casted from ribs, demonstrating the necessity of using this global map. If we remove the concatenation of the input to the intermediate channels, the model starts to generate hallucinated features and blurred fine details, indicating potential insufficient preservation of input information along encoding and decoding paths. If we omit the texture-friendly decoder blocks here and use transposed convolutions as in the previous work, checkerboard artifacts are observed here again. Finally, using random noise image input instead of learned Gaussian perturbation of feature channels, we can observe that the model is suboptimal at texture generation. We have also compared our method with the baseline method and SA2H, which uses the original generator. We also compare with our previous low to high image translation framework, which can be considered as a silver standard. We can observe that the baseline and SA2H fails to preserve anatomical structures and acoustic shadows, and also fail to generate faithful speckle texture. Compared to LSA2H, which has a low-quality image in input, our method is seen to be on par in structure preservation and has achieved even more realistic texture appearance. But our model cannot faithfully preserve anatomy in the structural complex region. For example, in this example, which has acoustic shadow around complex heart regions. To quantitatively assess the translation quality and realism, metrics like pixel-wise difference and SNR are often suboptimal due to the inherent noise speckle appearance of ultrasound images. Gang evaluation metrics, for example, FID score, can capture the realism in terms of texture. However, it only measures distance between two distributions and does not capture the local difference. To capture these local texture changes, we here introduce a sliding patch-based histogram metric. We compute chi-square distance between patch histograms on non-overlapping image patches. And here we show two sample spatial error maps for interpreting the local errors that are captured by p-chi-squared. The generated images of an SA2H have a lot of missing structures and therefore very high chi-squared error overall. In the top example, we see that the artificial skull enhancement in LSA2H and the hallucinated structures in the brain in SA2H invokes large error. And suboptimal texture appearance in LSA2H also leads to large chi-squared error. In the bottom example, there is high error of SA2H around the region of the complex heart. We can see that local chi-squared error well reflects our visual inspection. We have also used other standard metrics for evaluation, for example, PSNR, pixel-wise difference metric MAE. We report the average p-square error and also FID score for comparing the feature distribution using inception network. The significant performance drop in all four metrics of the ablated variance in baseline and SA2H demonstrate effectiveness of the proposed architectural changes. LSA2H has low MAE and PG-squared error compared to our method. Since our model struggles in complex regions as also seen from the previous example, and the low-quality input can certainly provide textural and structural pariah for those regions. Our model outperforms LSA2H in terms of FID, indicating better texture generation with our method. As demonstrated, our proposed method can translate directly from model slices to likeliness of high-quality rendering. However, it still has several limitations. First, Our method performs suboptimally in regions of complex structures overlaid with acoustic shadowing. Without actual physics guidance, for example from local simulation, ambiguous anatomy here may have problems for realistic translation. Second, we have considered and evaluated individual frames, but interactive ultrasound simulation requires temporal consistent images. Therefore, temporal consistency of sequences of ultrasound frames should be explored in future works. In this work, we demonstrate a gun-based approach for rendering B-mode images from cross-sectional model slices and integral attenuation map, which greatly helps generate faithful acoustic shadows. With the proposed architectural changes, for example, texture-friendly decoder, dedicated noise feeding, providing input to all channels, the present network in this work improves the translation quality in terms of both structure and texture. Our network runs at a constant inference time, and therefore the potential time gain can be arbitrarily large. It actually depends on the complexity of the target simulation. By bypassing complex rendering steps in real time, our approach warrants the use of sophisticated rendering and consumer hardware. Thanks a lot for listening.